This is our chapter 18 lecture on light, and you can see how excited I am about this chapter. It's one of my favorite chapters. We should first review some of the properties of light. We're going to look at light here as just a wave, even though there is wave-particle duality. And we want to talk about some ways that we characterize waves. The first one is amplitude. Amplitude is the height of the vector. There is wavelength. Wavelength is the difference or the distance from peak to peak. Technically, you could also do it from node to node. So that would be like the wavelength would be here also. And when we're talking about wavelength, the units should be some kind of length units there. So nanometers, centimeters, meters, those are pretty common. If it's nanometers, that's usually kind of in the visible range. Waves with meter-long wavelengths are more like the radio wave range. The next one on the list is frequency, and the symbol there is the symbol nu. It's not a V. And frequency is a little sometimes hard for people to imagine. It's defined as the number of oscillations that the wave makes each second or each amount of time. And that's technically a hertz. So a hertz is, when it's 1 hertz, it is 1 wave per second. Now, if we can do a little visualization when it comes to frequency. Okay, I want you to close your eyes and you're going to imagine that you're in the ocean. It's nice and relaxing, and you're kind of like bobbing up with the waves and then down as the wave passes you. Now, how fast, how many times a second you bob up and down would be your frequency. So that's basically the waves hitting your position. So if you're bobbing up and down very quickly, your frequency would be high. And how that relates back to wavelength is that if you're still imagining yourself bobbing up and down with the waves, as you go up, you're rising up with the wave, the distance between you and the next wave, like you can see the peak of the next wave, that would be the wavelength. Now, if you're bobbing up and down very quickly, it means the waves are hitting your position very frequently. And that means that the distance between the waves are coming much faster, the distance between the waves is going to be shorter. So that means that frequency and wavelength are inversely proportional. As your frequency goes up, you're bobbing up and down very quickly, the wavelength is short. And we just call that inversely proportional. Now, just as frequency and wavelength are inversely proportional, as one goes up, the other one goes down, they are also related to energy, and they're related to energy in this way. The energy of light, so that's E there, is related to the frequency, and this guy here is Planck's constant. And we have the value down there. I wanted to talk a little bit about these units. Planck's constant is a number, 6.626 times 10 to the negative 4, and then that is joules, and it should be joules times seconds, like that. When we look back at this equation, what it's saying is that the energy is equal to some kind of constant times frequency. So if the frequency goes up and you multiply it by a constant, the energy is also going to go up. So energy and frequency are directly proportional. There's one other thing that we should consider or talk about, and that is the speed of light. This is one way of writing the relationship between wavelength and frequency. This way over here is a little bit more common, and you might have seen it written in this format. What this equation is saying is that as the wavelength goes up, the frequency is going to go down, and they are related to each other with this constant, the speed of light in there. So the speed of light is not going to change for us, but as we change the wavelength, if we made it higher, we would see the frequency go down. If you were to take this equation and put that in for frequency, you would get this here. Okay, so that's a really common way of writing the relationship with energy, hc over the wavelength. And this variable right here, that is called the wave number, and it's written here. This little symbol over it, it's just basically trying to differentiate it from frequency. But wave numbers are the way that we label things. If you've ever seen an IR spectrum, an infrared spectrum of a compound, it's usually written in wave numbers. What's nice about wave numbers is it's the inverse of wavelength. So when the wavelength is really small, the wave numbers are kind of in the thousands place. So it makes a nice bigger number instead of having to write really tiny wavelengths like 10 times 10 to the -6, you could write something like, 6,000 wave numbers. So it's just a little way of changing things up so that it's easier for people to kind of comprehend when they're looking at a spectrum. All right. So when you take OCHEM, you're going to see these wave numbers. But for us, we are going to stick to frequency and wavelength and energy just the way they're written here. To put things in perspective, I thought we should look at the relative lengths of waves. So I'm going to be looking kind of at this part of the spectrum here. So the way this picture goes is on the right-hand side, these would be very short wavelengths, and on this side it would be very long wavelengths. So that would be like the scale, the size of Mount Everest on this end, and then an atomic nuclei on this end. And I wanted to point out that our visible light is kind of in this range here, and our visible light has a very short span to it. So what we can see with our eyes is a very small part of this whole spectrum. On the kind of lower energy side, we have infrared light, so that is lower energy than what we can see. On the high energy side, we have ultraviolet light. This is just a slightly different picture where I'm still looking at wavelength here. And on this side, the long wavelengths are on this side. So these are long wavelengths, and these are shorter wavelengths. And our visible light is right here. And like I was saying, on the lower energy than our visible light, we have infrared, and on the higher side, we have ultraviolet. So this is high energy, short wavelength. This is low energy, long wavelengths, because those are inversely proportional to each other. And when we're going to talk a little bit about visible light, but I wanted to kind of describe what's happening with infrared light and describe what's happening with ultraviolet light. For infrared light, we're actually looking at the difference in energies of vibrations between atoms within a molecule. So we're looking at the molecule changing energy due to vibration. Visible light, in this range here, has to do with electrons being excited to higher energy levels within atoms. So we'll talk a little bit about that. And then ultraviolet is basically a stronger version of that excitation. So we call that electronic excitation. Now when I say ultraviolet radiation or ultraviolet light is a stronger version of that excitation, I just mean a higher energy version of that. If we keep on going to the higher energy side from ultraviolet, we will eventually get to X-rays, and X-rays are waves that have so much energy that they can actually cause bond breakage, and they can cause ionization. That's when an electron is stripped from an atom. And that's the reason why X-rays are so damaging to our skin, is because they cause these processes to happen in our cells on our skin, and that is definitely not good for our skin. It's what causes a sunburn. If you keep on going up in energy, you will eventually get to gamma rays, and gamma rays are extremely high energy waves. They are very damaging to almost everything living. The good news is gamma rays are extremely few and far between. There's a higher incidence of gamma rays when there's things like a solar flare, but in general, we don't get hit with them very often, which is good for us. Now, if you're thinking about what these waves of light look like to us, of course, we can only see visible light. But even visible light kind of is interesting in the way that what our eyes perceived compared to what's actually happening. And I kind of want to look at this table that we have here. And what's on it is color absorbed and color observed. When you think about something that is, say, red, so if we observe something that's red, the reason why we see it as red is because it is absorbing all of the blue and blue-green light. So if you were to plot what wavelengths certain compounds absorb, it's basically the opposite of the color it looks like, the color that we're observing. Now, when we do our iron in spectroscopy lab, we're going to see a solution that is very orange. And when we look at its absorption spectrum, basically the wavelengths of light that it absorbs the most, we will see that it absorbs in the blue range, which is kind of in this wavelength range. So about kind of in the mid-range of the 400 nanometers. So let's think about what happens when our compound absorbs light. If it's in the visible range, it's due to electronic excitation. And what's happening there is that the electrons and the atoms are in some kind of ground state, the low energy state, and we shine some light on the atoms, and the electrons absorb some of the light. And when those electrons absorb light, they go to a higher energy level. That higher state is called the excited state. And what's interesting is we can basically shine a whole spectrum of light on a compound and measure what it absorbs and what it doesn't absorb. And what it absorbs tells us about these two energy levels. So if we can figure out what kind of light a compound will absorb, we will know what kind of energy a compound will absorb. And the energy that it absorbs is equal to the difference in the energy levels. So this would be the ground state, and this would be the excited state. So by monitoring the kind of light that something absorbs, we can actually tell about the energy levels within the atoms in the compound. This also means that we can use that light to tell the difference in compounds. So different chemicals have different electron shells, which means that they are going to have different energy levels. And that means that each one absorbs their own particular type of light. And we basically call this a fingerprint. So we we can measure what kind of light a compound will absorb, and we use that as a fingerprint to identify it later. Now, if you're using the slides, I skipped ahead a little bit because I just wanted to show you what some absorption spectrums look like. They look like these over here. So on this side, it's intensity. On this bottom part, so this bottom part along the bottom here, it is wavelength. And so what this spectrum is showing on the top here is that beta carotene doesn't absorb very much at really low wavelengths, but as we get into higher wavelengths, it gets higher and higher, and then there's a dip and it's going down. So anytime we see a spectrum that looks just like this, we know that there's beta carotene there. Now caffeine looks much different. It's a nice curvy one, and its peak is somewhere around, 275, something like that. That's very different than beta carotene, which has kind of like two lobes, and it's maybe at 440 and 530 or something like that. But things can get a little complicated when you have a mixture of compounds, when you don't have things isolated. If you can look at this spectrum here and this spectrum here, if you added them together, you notice that the peak here is maybe about 280 and the peak here is about 270. So I'm going to take this spectrum and kind of draw it in here. It would be something like that. Now if I add those two spectrums together, it would look like this. That red wouldn't be there. So if I saw a spectrum that looked like this, all filled in, it would be hard for me to know that that isn't a new compound and not caffeine added to aspirin. So when we say that compounds have a fingerprint, that's true, but if you put a lot of fingerprints on top of each other, it's hard to know whether it's a new fingerprint or it is just fingerprints added together. All right, so that's why when you have a mixture of things, and you know what compounds are in there and you're trying to monitor how much of each one is in there, you want to pick a wavelength for each compound that is very different than the other compounds. For example, if I want to look at acetone and beta carotene, I could see that the acetone peak is at 270, and that is, like, if I'm comparing that to beta carotene, that is way far even out of the spectrum. Beta carotene is at 450, so I could actually monitor those two wavelengths individually. I could use the 270 to monitor the acetone and the 450 to monitor the beta carotene, and they would not interfere with each other. So now I'm going to go back into the slides from when I jumped forward. So once we've identified what kind of wavelength we should use to monitor a compound, okay, we always want to pick something where it has a very high absorption so that it's easy to measure. But once we've identified that wavelength, there's some other things that influence how much light something will absorb. And in this picture that we have down here, we have different concentrations of an iron compound. This is going to look very similar to what we're going to see in our spectroscopy of iron lab. On this side, we have low concentration. So I'm going to say low concentration. On this side, we have high concentration. And just kind of visually, we can see that that's true. This one is so much darker than this one. Now, when we say darker, what we're really saying is that it is absorbing more light. One on this end is absorbing less light. This one on this one is absorbing more light. Now, how much light something absorbs has a couple components. Okay, so we're going to say that the light absorbed is A. And it is dependent on how much distance the light must pass through the sample. That's basically saying the thicker the sample, the more light that's going to be absorbed. Something else that we need to consider is the amount of absorbing chemicals in the sample. If the sample is more concentrated, it's going to absorb more light. And the last thing is we need to consider how well the sample absorbs light, and that's called the molar absorptivity. It's a inherent characteristic of the compound, so in this case it's the molar absorptivity of iron in solution. And when the molar absorptivity is high, it means that that thing is really sensitive to light. It absorbs a lot of light. If the molar absorptivity is low, it means that no matter how much light you shine on it, it only absorbs a very small percentage. Now, when you put these three factors into an equation, you get this one here. What that's saying is that the absorbance is equal to the molar absorptivity, so that's this guy here, the cell length, which is how thick the sample is, and then the concentration of the solution. Now, anytime any one of these goes up, the absorption is going to go up. All right, so if we make the concentration higher, the absorbance is going to go up. If we make the sample thicker, the absorption is going to go up. And if we somehow change the molar absorptivity, like if we compare one compound to another and one has a higher molar absorptivity than the other, the absorbance of that compound is going to be higher. All right, this equation is known as Beer's law, and it's the way that we use light to measure concentration. What we do is we monitor the absorption and we calculate the concentration. When we say that we observe absorbance, what we're really saying is that we shine some light where we know the intensity of the light, and we shine that light on a sample. We know the intensity before the sample, and then we measure the intensity after the sample. And the difference between those is how much has been absorbed by the compound. Now, we can look at it like this, where the absorbance is the negative log of P. P is the intensity after the sample. PO is the intensity before the sample. So the difference between those is how much light has been absorbed by the sample. And that ratio of the intensity before and the intensity after is actually called the transmittance. So when we look at transmittance, really what we're looking at is how much light has been transmitted through the sample. So imagine this is our sample here, and we're putting some light in, and I'm going to call that PO. So that's the intensity of light going in, and the intensity of light coming out is P. P, the second one, should be lower because some of the light has been absorbed by the sample. So when we kind of think about what that means for this ratio here, P is always going to be the lower number, P naught is going to be the higher number. So transmittance is always going to be a number that is less than 1, okay? If it was 1, it would mean that no light, it would mean that all the light was transmitted through the sample, and that basically would mean that our sample was not sensitive to light and we should not be doing spectroscopy experiments with it. So our transmittance is always going to be lower than 1, and we don't want it to be 0, because 0 would mean that no light made it through the sample, right? So we want some kind of transmittance of between 0 and 1, closer to 0. That would mean that it was very sensitive. Our sample was very sensitive to light and absorbs a lot of light, and that would mean that the molar absorptivity would be high. So now we're back to the slides that I kind of skipped ahead to, and we have a bunch of absorption spectrums here. And what these absorption spectrums are really telling us is what wavelengths those compounds are most sensitive to. Where is the transmittance the lowest and the absorbances the highest? We use these absorption spectrums, again, to pick what wavelengths we should measure for each compound. So what you do is you use an absorption spectrum, you pick your wavelength, and then what you can do is you can monitor solutions at this wavelength, and you can use the intensity of light that is absorbed by the compound to determine its concentration. One of the most common ways of doing that is to build a calibration curve. All right. Now the idea, remember, of a calibration curve is that you measure a bunch of known solutions and find some kind of reading to monitor them, and you build this calibration curve of those known solutions so that you can find the concentration of an unknown. And when we're looking at this calibration curve here, they were monitoring a solution at 562 nanometers, so that's the wavelength that they were measuring at. And they measured a solution that was 2 micrograms, so 2 micrograms. They measured one that was 3 micrograms of iron. They measured one that was 5. They measured one that was, looks like 6, maybe 7 or 8 and 9. They measured all these solutions, and then they made a best fit line through them. Okay? And then they measured the absorbance. So they measured the absorbance of an unknown solution. So they measured the absorbance, and then they went over to the calibration curve, and they went down, and you would see that the unknown solution was somewhere between 3 and 4 micrograms. So maybe it's, I'm just kind of estimating there, but it's maybe 3.8 micrograms. Now remember all the things we said about calibration curves? When you're running a calibration curve, you want your calibration points to be close to what you think your unknown is going to be. We don't want to use a calibration curve like this and then somehow get our unknown have an absorbance of way up here on the graph, okay, and then way up here on the graph, and we don't really have any data. We don't have any data points up there. We don't have any standard solutions to represent what the calibration curve looks like up that high. So we always want to pick calibration points that are spread out from each other, but somewhere close to what we think our unknown is going to be. And if we miss it the first time, if we have a calibration curve like this, and then we measure our absorbance and it's really high, and we don't have any standard solutions to represent the calibration curve up there, then we would rerun our calibration curve with standards that were more in this range. When we're thinking about Beer's law, I just want to kind of point out a few limitations to Beer's law. One of the biggest ones is that at high concentration, the solute molecules influence one another, and we get a nonlinear curve for absorption up at high concentrations. And that's one of the reasons why we want to keep the absorption into the 1 to 1.5 range. That means between 80 and about 3% transmittance. So again, I was saying we don't want it to be 100 transmittance. So 100% transmittance, that would mean that all the light was being absorbed and there's nothing to monitor. And we don't want it to be 0 transmittance, because that means that our compound is not sensitive to light at all. And so observing light isn't really a good way to measure a change in concentration. Now, all the things that I've been talking about, I've been saying solution, because a lot of times we're monitoring the absorbance of a solution that contains an analyte that we are interested in. So, for example, in our spectroscopy lab, we're going to be interested in iron, but it's really aqueous iron ions in a solution. And the solution itself absorbs some light. So if we think about this curve that we have down here, this absorption spectrum, imagine that this is the absorption spectrum of our solution, like the water and the other things that we have that are kind of in the background. And this one is the absorption spectrum of our iron. When we're trying to pick what wavelength to observe so that we can monitor the iron, what we want to do is pick the highest peak for the iron, okay, because that's where the the iron is most sensitive to light. What we don't want to do is pick a wavelength that is that equally represents both of our things that are absorbing. So if we pick something in, like, say, the 470 range, which is right about here, we're observing the iron spectrum, but we're also observing our solution spectrum. So when we look at the different parts of this kind of combined spectrum, this wavelength would be good for our iron. This wavelength, so this wavelength here, would be good for maybe, say, the water or the solution. And this wavelength would be not good for either one of them. So now let's do a little practice with actual Beer's law. So I'm just going to remind you, Beer's law says that the absorbance is equal to the molar absorptivity times the path length, so that's the thickness of the cell, times the concentration of the compound. Okay, so let's read this problem here. It says that we have a concentration of a solution of compound A exhibited at an absorbance of this at, and this is the wavelength. So that's my absorption, and the wavelength is 238 nanometers. And then it says a 1.00 centimeter cuvette. That word cuvette, if you haven't heard that before, a cuvette is usually a small glass or quartz container. They are rectangular in shape like this, and you fill your solution with them, and then you shine your light in one side and the light comes out the other, and an instrument called a spectrometer records the intensity of light going in. So it has the intensity of light going in, and it has the intensity of light going out. But the cuvette, in this case, represents the thickness of our cell. So that is B, the path length or the thickness of the sample. So this 1.00 centimeter cuvette, that represents our path length, our B. Now the problem also says a blank had an absorbance of 0.029. And the reason why that's important is because the blank represents the solution that our analyte is swimming around in. And so our analyte is only absorbing the difference between these two numbers. If you think about it, this 0.624 here, that is the absorbance of our compound and the blank. Okay, so the solution that it's swimming around in. We need to subtract out this absorbance of the blank to find the absorbance of our analyte. I'm going to finish reading the problem here, and then we'll go back to that information. Okay, it says the absorbance of an unknown solution of compound A was 0.037. Now, when I put this information together, I'm measuring absorbance, so I know I'm going to use Beer's law. Right. And I'm given the absorbance, so I have that one. I'm given the cell length, the 1 centimeter cuvette, so I have that one. I'm trying to find the concentration of A in the solution, so I'm trying to find this one here. I can do that if I somehow knew the molar absorptivity. The problem does not tell me the molar absorptivity, so I'm going to go back to the problem and I'm going to figure out how I can find it with the information that's given. So looking back at the beginning of the problem, I'm given a concentration, I'm given a path length, and I'm given an absorbance. So I'm given an absorbance, I'm given a path length, and I'm given a concentration. So because I have each one of these things, I can find the molar absorptivity. And once you find the molar absorptivity, I can put it back into my second set of information where I'm given the absorbance, and then I can find the concentration. And that's what I'm going to do. I'm going to first find the molar absorptivity, and I'm just going to show my work right down here. So I'm going to take the absorbance, the path length, the concentration, and I'm going to find molar absorptivity. If I do a little algebra, I can set it up like that. And now I'm going to put in my numbers. So I have my absorbance, but remember, we need to subtract out the absorbance of the blank. So when I set that up, it's going to be 0.624 minus 0.029. So that's the absorbance of our concentration that we know minus the blank. The path length goes on the bottom. That's centimeters. And then the concentration is 3.69 times 10 to the negative 4th molarity. And on my calculator, I got 1.503 times 10 to the third here. Let's think about units. There's nothing on the top. Absorption is a unitless number, so there's nothing on the top, but on the bottom, there's centimeters and molarity. So this is actually centimeters times molarity. Sometimes you see that written as molarity, molarity to the minus 1, centimeters to the minus 1. That's saying the same thing. Okay, and that is our molar absorptivity. So now we can use that molar absorptivity to solve for the second part of the problem, which is really what we're trying to find. We're going to put in the molar absorptivity. We know that the path length is 1. We know that the absorbance is 0.375. Now we can find the concentration. Okay, I'm going to show my work up here. I'm going to use Beer's law again. I have my absorbance. I have my path length, which is the same cuvette. I'm trying to find the concentration, and now I have the molar absorptivity. When we look at units, centimeters and centimeters are going to cancel out, and I'm going to get 1 over molarity on one side. When I do the algebra, it's going to come out to be molarity. Okay. One thing that I wanted to mention is that I just wrote this as the absorption, like this, but I should really subtract out my blank because the blank is contributing 0.029 to this. So it should really be 0.346 equals 1 centimeter. Like this. Alright, so algebraically what I'm going to do is I'm going to divide both sides by this. And that actually had canceled out, so I don't even need to deal with that. And I'm going to divide both sides. This. Alright, so those cancel out. I'm not even going to do anything with the 1 because it's just a 1, and it's not going to change the math. So when I put this into my calculator, I got 2.30 times 10 to the negative 4th molarity. And the reason why I'm saying molarity is because I'm taking 1 and I'm dividing it by 1 over molarity. That equals molarity. So I'm taking the inverse of the inverse there. And that is equal to my concentration, the only thing left on this side. All right, so we have found the concentration of an unknown solution by monitoring some absorbances and knowing the concentration of a standard. All right, so just kind of review what we talked about in this little lecture is we started with talking about the characteristics of light. We also talked about how you can use the path cell length and the concentration and molar absorptivity to find absorbance, or how we did it is we, in our problem, we used absorbance to find concentration. You can do that too. That is called Beer's law. We talked about absorption spectrum and how you can use different wavelengths to monitor different compounds. We kind of touched on calibration curves. And we also talked about how you can do some math. You can use the absorption, the path length, the molar absorptivity to find concentration. With all that said, I hope you realize how important light is to observing different compounds, and how it's a pretty powerful tool when we're trying to find even really minute concentrations of compounds.